All right, we're going to talk about exponential growth and decay. As you can see here, this is a formula that's supposed to represent exponential growth, and this is a formula that's supposed to represent exponential decay. And you can see that the two formulas look very similar. What I'd like you to do right now is pause the video and write down growth and then the formula and then decay and then the formula. And when you're caught up to me, I'll continue. Okay, hopefully you paused the video and you got that all written down. What we're going to do is I'd like to define some things. When you look at this formula, this letter A usually has a distinct meaning in an exponential growth or decay equation. Usually the A is the initial amount. Or if you prefer the starting amount, whatever words make you happy. The other way we could say it is this is the amount when t equals 0. Okay, so that's an important idea. The y is the y is, let me think about this. Yeah, Oh, I know what I was concerned about. So if this is the amount when t equals 0, and this is the initial amount, you might be asking yourself the question, initial amount of what? Well, for exponential growth, it could be money, it could be bacteria, it could be a whole bunch of different things. It could be for growth, it's probably not anything radioactive, but money grows, bacteria tend to mate and grow. This could be the number of zombies you start with, or the number of people that have the flu, or the number of people that have some other transmittable disease. Okay, so this y is usually the final amount, or we could just say the amount at time t. So if you're given a certain amount of time, the y will give us the amount of stuff that you have, like the number of people or the amount of money, at time equals t. In other words, if we're given a certain amount of time, like 5 years or whatever, and we're given the initial amount and the growth rate, r, oh, oops, we better nail that one down too. This r right here, that guy is known as the growth rate. Now, it's the growth rate when we're adding 1 to it, okay? Over here we have an r also, and this r is the decay rate. And it's the decay rate when we have 1 minus that value. And what are values that r can assume? R is like a percent. When we do math with percents, we'll write it as a decimal. But r could be like 0.05 or 0.75, and r could be like 0.25 or 0.07. And then when you do 1 minus that, you get a decay. And if you do 1 plus the growth rate, then you get growth. Okay, so that's kind of the gist of how these formulas work. Maybe we can try a little math. So let's say that we had some money, and let's say we had $1,000. Why not, right? And we wanted to invest that money, and we wanted to earn more money. So we went to the bank, and we discovered they were going to give us a 3% interest rate, which, between you and me, that's unheard of these days. It's a little on the high side, which is sad. You should be able to get interest of 3% or more easily, but we don't. Anyways, let's say you go to the bank and you can get 3% interest on your $1,000. We would write it out as $1,000 is our initial starting amount, 1 plus the 3%, we write 3% as a decimal, and then let's say you were able to put that money away for 5 years. So I'll write t as 5. Then what we can, as long as the interest is compounded annually, then this 5 stands for years. And so we can go ahead and, if we do the math, whatever we end up getting for y, that will be the amount of money that we have in the bank after we deposit initially $1,000 at 3% interest for 5 years. So I just wanted to give you a feel for how the formula works. Okay, on the other hand, oh, by the way, I didn't tell you what A and Y were here because they're the same as over here. A is the initial amount, Y is the amount at time after time t. And t is amount of time, and it's not always in years. It could be in minutes or seconds or nanoseconds or hours or months or weeks or whatever. But in our case, we're going to use it as years. And so I'm going to say, I'm going to talk about car depreciation. Let's say we buy a new car today and we spend $30,000. Because why not, right? We're rich. Or at least in the realm of math, homework, and lessons, we can at least fantasize about being rich. So 30,000 bucks is our initial cost. But the problem is, as soon as you walk off the lot, as soon as you drive off the lot with a new car, it goes down in value. So let's say that we analyze a bunch of data over the years. We go to the website AutoTrader, and we discover that when if you buy a car, if a car is dated 2017 and it's $30,000, we see a car that's dated 2017 and it is $30,000. But we see a car that's dated 2016 and it's less, and 2014 we see another car that's just like it and it's worth less. They're selling it for less. And we see a car that's dated 2010 and they're selling it for less. We could calculate what the decay rate is, and let's say the rate of decay is 8% or 0.08. Then to calculate what our car would be worth, this $30,000 car that we buy today, if a reasonable decay rate for a car depreciation is 0.08, we could just figure out, well, how long do we think we're going to hold on to the car? Let's say we're going to hold on to the car for 3 years. Then we could go ahead and do the math and we could figure out what the car will be worth if we spend $30,000 today and there's an 8% decay rate and it goes for 3 years. This formula will do the math for us. All right, I just wanted to give you a quick overview of this whole YA1RT thing.